Today we're going to talk about entropy, and we're going to continue our discussion of Chapter 8. When we looked at entropy, we looked at the idea that it can be used practically, and we have a philosophic meaning to it as well, that where we use it in that regard. So we'll be examining both of those today. When we initially looked at entropy, with the symbol S, we looked at the idea that Clausius used this as a property to determine whether a system was in equilibrium, and we looked at the different types of equilibrium systems could be in. And if you recall, we had something called stable equilibrium. And with stable equilibrium, it's like the ball in the bottom of a bowl, and if you move the bowl a little, the ball always goes back to the bottom. We have metastable, where we have the ball in a depression, and we can move it a little, but if we change the system a lot, the system will move out of equilibrium. So this is called metastable equilibrium. And then we have the idea of sort of like balancing on a pencil point, but in our case with the ball, we'll turn the bowl upside down, and we'll have the ball here, and this is unstable equilibrium. And so with unstable equilibrium, it's very precarious, and any slight change will cause a dramatic change in system behavior. And so when we looked at this, Clausius was interested in this in terms of determining whether the systems were in one of these states. And with that, he developed and thought about the property of entropy. So he developed something, and in the book it goes through a rigorous development of this, which I will not do here, that led to the Clausius inequality, which forms the basis of the second law of thermodynamics in terms of its entropic formulation. So with the second law, the Clausius inequality, we have that the cyclic integral of del Q over T is less than or equal to 0. And so with this, we can apply this cyclic integral. So we can apply the cyclic integral to a cycle of two processes. So on a PV diagram, we'll go from state 1 to state 2. We'll have point P, start from 1, go to 2, along path A, and then we'll go back along path B. And what he's looking at is what happens as the system goes this way, or if the system reversed itself and went the other way. And we want to be able to apply this Clausius inequality in both directions. Notice in this case that I drew a solid line, which means that it's a system in equilibrium, so it's a reversible processes. So paths A and B are reversible processes. So with that, if I apply the inequality to these paths, we end up with the path from 1 to 2 of del Q over T along path A is equal to the same del Q over T along path B is equal to a constant. And if we look at this, this indicates to us that del Q over T does not depend on a path. And that's the definition of a property. So the del Q over T is the definition of a property, and we'll call that property the change of del S. So del Q over T means property definition and we'll call del Q over T ds the change of entropy. So we end up with this important feature for reversible processes. If you recall, we had a similar situation when we looked at work. So when I looked at work, I had that del W was equal to PdV, or del W over P is equal to dV. So this is analogous where we have an inexact differential or a path function. So del W is a path function. Del Q is a path function, and 1 over P and 1 over T convert this path function energy form into a property. 1 over P and 1 over T convert del W and del Q into properties. So with that then, I have that del Q is equal to TdS for reversible processes. And I can integrate this just as I could integrate del W as PdV. And I have del W is equal to PdV. So I can apply this to systems. So if I look at a reversible adiabatic process, so now let's examine this equation in a little more depth. If I examine it in a little more depth, I have that del Q is equal to TdS, and for adiabatic processes, del Q is equal to 0. This function is for reversible processes only. So for reversible adiabatic, ds equals 0, or s equals a constant, or s large S equals a constant. So we have reversible adiabatic means constant entropy, and we also call this an isentropic process. So with this, we're going to apply this to first law equations in just a second, but I wanted to determine the expression for the change of internal energy of an incompressible substance, such as a liquid or a solid. And so when we look at a liquid or a solid, we need to develop an expression for the change of entropy. We had developed an expression for change of entropy, for entropy and the change of entropy for an ideal gas previously, and we had looked at the tables of properties for pure substances and found where to find entropy and its manipulation there. So for incompressible substances, solids, and liquids that are not pressurized too much, we have that the internal energy is a function of temperature and specific volume. V is equal to a constant for incompressible. Therefore, U is equal to U of T, and I end up with the expression that du is equal to C dt, where C is equal to the specific heat. If I then look at, so we can use this to determine the internal energy change for a solid or a liquid. There is no difference for a solid and liquid between U and H, so they're the same property. So we're not distinguishing between enthalpy and internal energy. If we want the internal energy of a solid, we can find its change here. If I look at the expression for the first law, del Q is equal to du plus del W, where del W is equal to PdV, dV is equal to 0, and so TdS is equal to C dt, or ds is equal to C dt over T. And if I integrate that, I have the integral of ds is equal to the integral of C dt over T. We have that S2 minus S1 is equal to C times the log of T2 over T1. And so we can use this form for the change of entropy for a solid. Let's look at an example looking at knowledge we have using entropy with heat, so we begin to understand how useful this property can be. So here's an example where we're going to heat water at a constant pressure. So we're going to heat water at a constant pressure from a saturated liquid to a saturated vapor. So we're going to heat 2 kilograms of water from a saturated liquid state to saturated vapor at 1000 kPa. So basically in this situation, I take this as our piston cylinder, it's going to expand at P equals C, and in here I have 2 kilograms of H2O. And basically we're providing heat to do that. So the physical understanding of what's going on is I have 2 kilograms of water, I'm going to heat them so they go from liquid to entirely vapor. This is going to rise at constant pressure. And on the TS diagram, a line at constant pressure looks like this, and we're going from state 1 to state 2. And this is constant pressure. So we know that for a closed system, so we have a closed system, we have energies involved, we have the substance is H2O, and the process is P equals C. And we know then that Q is equal to del H is equal to M times H2 minus H1. And so what we want to do is find the properties of H1 and H2. So H2 is equal to H sub G at 1000 kPa. H1 is equal to H sub F at 1000 kPa, and H2 minus H1 is equal to H sub Fg, so I really only have to look up one term, and so Q12 is equal to 2 times H sub Fg, and if I look that up, it's 2 times 2015.8, and so I have that Q12 is equal to 4031.6 kilojoules. But notice as well that del Q is equal to TdS. So if we look at the process from 1 to 2, it's also constant temperature. So therefore, the integral of del Q from 1 to 2 is equal to 1 to 2 of TdS is equal to T times the mass times S2 minus S1. So now let's look this up and calculate this, and notice that this is the area under curve. So if I look at the area under the curve on the TS diagram, this represents the heat from 1 to 2. So one of the powers of using the TS diagram is that I'm representing heat as an area, just as I had work as an area on a PV diagram. So I have heat as an area, and let's calculate and see if we get the same number using the equation with the entropy formulation. So Q12 is equal to MT times delta S, and delta S is equal to S sub Fg. So Q12 is equal to 2 times the temperature, 179.88 plus 273.15. So it's degrees K times S sub Fg, which is 4.4496. And we end up, of course, with the same result. Q12 is 4,031.6 kilojoules. So I now have a way of using the entropy formulation to find heat. And I can also find heat using the traditional methods that we had developed from chapter 6. What we'd like to look at now is moving into a little more philosophy aspect of using entropy. So in this case, we were able to find the change of entropy. So we've looked at various ways to find the change of entropy. So if I can highlight this, so we have the entropy change for an ideal gas, which we covered initially. So I have, for an ideal gas, we had two formulations for S2 minus S1. One was equal to mc sub p times log of T2 over T1 minus mr log of P2 over P1. And the second one was in terms of temperature and volume. So we had mc sub v times the log of T2 over T1 plus mr times the log of V2 over V1. So we had these for an ideal gas. For a pure substance, we have that S2 minus S1 was equal to m times S2 minus S1. And we get these from the tables. So we have the ability to calculate the change of entropy for an ideal gas and a pure substance. Entropy is a property, so it doesn't depend on system path. So we have a way to do that. Now what we're going to do is change the Clausius inequality to an equality and introduce a term called entropy production. So we're going to change the Clausius inequality to an equality. And to do that, we're going to be looking at introducing an idea of entropy production. So we have the cyclic integral of del Q over T is equal to less than or equal to 0. And I can make this an equality by introducing the idea that del Q over T is equal to minus delta S production. So this is an arbitrary constant that I introduced, and it's called entropy production. We have a minus sign here. And we're going to see the following, that del S production is equal to 0 for reversible processes, and del S production is greater than 0 for irreversible processes. And so it's a measure of how irreversible the process is. Del S production is a measure of process irreversibility. So now I want to apply this. I'll apply this to a two-path cycle, one made up of an irreversible process, one made up of a reversible process, and we'll see what evolves, and we'll then use this in an example. So we're going to apply this to process here. So I'll go on a PV diagram. We're going to go from 1 to 2 along an irreversible process. In an irreversible process, I don't know the path, and then we'll go from 1 to 2 irreversibly, and then reversibly where I know it. So we'll denote the processes by I for irreversible, R for reversible, and I'll be applying the cyclic integral to that. So if I apply the cyclic integral to that, and I'll do it here so I can have everything flow underneath itself and not run out of board space. So if I apply it here, we have the integral of del Q over T along an irreversible process plus, so we went from 1 to 2, now we're going to go from 2 to 1, del Q over T along a reversible process, and this is going to be equal to minus del S production. So basically I'm going to bring this over to the other side and change the limits. So I'm going to change the limits. And when I do that, it changes the sign. So if I bring this over to the right-hand side and this over to the left-hand side, I'll have that 1 to 2 of del Q over T irreversible plus del S production is equal to the integral from 1 to 2 of del Q over T reversible. We know that this is the definition of entropy change. So this is equal to S2 minus S1. And so I have an expression for the change of entropy, including the entropy production. Now normally what we do is we have the change of entropy on the left-hand side, so if I just move that around, so I have it over here, I have S2 minus S1 is equal to 1 to 2 of del Q over T irreversible plus the entropy production. And this is an expression for the second law for a closed system, so I have a way to express that. You know how to calculate this. So one of the things that sometimes happens is that people become bothered by looking at this, that they don't know anything. You know how to do this. You calculate this for an ideal gas or a pure substance. So I know how to calculate that. So you've had practice doing that. And now let's explore this a little bit more. And so what we do is we basically change this. I can make this a summation of different heat flows into or out of the system. So if I look at a system, and here's the system, I'm going to look at Qi at Ti. So I have heat flow, and this is heat flow into the system at a temperature, the surface temperature Ti. So Ti is equal to the surface temperature temp of our system, and therefore I can have that S2 minus S1 is equal to sum of Qi over Ti plus del S production. So if I don't have any heat flow, the change of entropy is equal to the entropy production. Let me say that again. If there is no heat flow, then del S is the entropy production. That's how we can, it's that simple. We tend to get a little baffled by this, but let's apply this a little bit more. So now what I'd like to do is look at a system, two systems interacting with each other. So I'll have two systems, system 1 and system 2. So I now am going to say that subsystems 1 and 2 interact. And I'm going to draw a boundary around them. And when I draw a boundary around them, they're the only two things that are interacting. There's no other interaction going on. So they form an isolated system. And I can calculate then delta S for system 1 and delta S for system 2. I know how to do that. So I can calculate delta S1 and delta S2. We know how to calculate that. What the second law is going to tell us for an isolated system that the sum of the del Si is going to be greater than or equal to 0. And the sum of the del Si is your entropy production. So it will tell us the entropy production, which is created by any energy change between these two systems, these two subsystems in the total system.